All right. So, okay. So we are back. Thanks, Justine. Great offer. So sadly, since there's no one to share it with, I guess I have to do Coke alone. So if I start talking really fast and then going too fast, then you're not understanding what I'm saying and everything's going like that, it's just because my mind is so engaged in this course material. What Ella said. I want to, yeah, Ella can see Emily do a cartwheel. There's no one here to watch out for me, to dial 911, to record it, to show it to, you know, the hospital and go, this is what he did, and that's how he hurt himself. And then they can laugh. So, I wanted to say that in terms of announcements, the key to problem set 7 has been uploaded to Facebook. No, it hasn't been uploaded to Facebook. What a morning. The key to problem set 7 has been uploaded to Blackboard. You're not here, Justine. You can't do first aid via remote. Whatever. If you want, I'll upload the key to problem set 7 to Facebook too, but whatever. I've had way too much Coke. Way too much. Moving on. Last day, we did have a glitch, and for whatever reason, I got kicked off of Blackboard, probably because I was on Facebook. I don't know. Whatever. I got kicked off last 4 minutes. I did upload the complete course notes to Blackboard. Or sorry, no, I didn't even upload it there. Uploaded it to YouTube because Blackboard would have had nothing. And so it is up on Blackboard. I'm not going to go over the material just because I want to keep moving forward. We are going to do one more example in class, but this is what ended up happening last day. I ended up solving these expressions. Oh, actually, I should go to here first. And I did parts A and B on the notes under basic conditions. And this is what the answers were that we would have gotten, that you'll find on the uploaded YouTube channel. I'm going to do one more just to finish it. Did anyone actually work through the last two on the question? Did anyone actually do parts C and D? Take that as a no. I'm going to do C just to do one more example, and then we're going to move on. So, and I actually don't have C worked out. So C has the reaction Fe3 plus NH4OH. Actually, I'm going to do D because it's under basic conditions. So I'm actually going to do D. It's under basic conditions. And that's what you didn't see last day. ClO2, aqueous, plus, reacts to give ClO3 minus, plus Cl minus. And this is under basic conditions. All right. Assign oxidation states, -1, -2, that makes that +5, -2, +4. So redox couples are there. We have ClO2 reacting to give Cl minus, and we have ClO2 reacting to give ClO3 minus. All right, in terms of the first one, to balance, mass is balanced for chlorines, but not for oxygens. I need to add 2 water molecules there, which means I need to add 4 hydrogen ions to the left-hand side, so that's good. So mass is now balanced. To balance the charge, I've got 4 plus on the left, I've got -1 on the right. And so that is actually a 5 electron transfer process. In terms of the second one, and you can verify that, just by the way, +4 to -1, that is a difference of 5. For the second one, I'm actually going to need a water on the left-hand side. That's going to give me 2 hydrogen ions on the right-hand side. And then in order to balance the charge, I'm going to need 1 electron. Okay. In order to get the electrons to cancel out, I'm going to need to multiply through the second one by 5. Electrons are going to cancel. Some of the hydrogens are going to cancel too, and some of the waters are going to cancel. So you're left with 5 plus 1 is 6 ClO2 plus 3 water molecules reacts to give 5 ClO3 minus plus Cl minus plus 6 hydrogen ions. And just to confirm mass and charge balance, 6 chlorines, 5 plus 1 is 6 chlorines, 6 times 2 is 12, 15 oxygens, 5 times 3 is 15 oxygens. I've got 3 times 2 is 6 hydrogens, 6 hydrogens. Mass is balanced. On charge, the left-hand side is neutral. The right-hand side is 6 minus plus 6 plus, which is neutral. So done. Good deal. I'm going to leave the C as an exercise, but just to give you the answer, 4Fe3 plus 2 NH3OH plus reacts to give 4Fe2 plus N2O plus H2O plus 6H plus. All right. Does anyone have any questions on that?
Roy,
Yep, go ahead, Dara.
if part B was in a basic solution, how can
Oh.
you add OH to this?
Thank you very much, Adara. Greatly appreciated. I forgot to change part C to basic solution. So I'm going to try doing something here and see if this is actually going to work. Hey, it did. Sweet. Space. Thank you, Adara, for pointing that out to me. This is under basic conditions, and we do need to convert to basic conditions. We've got 6 hydrogen ions. In order to convert to basic conditions, we just add 6 hydroxides to both sides. This becomes 6 water molecules. And we can see a cancellation between the 3 water molecules and 3 water molecules there. And so under basic conditions, thank you, Adara, 6 ClO2 plus 6 OH minus reacts to give 5 ClO3 minus plus Cl minus plus 3 water molecules. Thank you, Adara. Just to verify, 6 chlorines, 12, 18 oxygens, 5 times 3 is 15, plus 3 is 18, 6 hydrogens, 6 hydrogens. Charge is 6 minus and 6 minus. Yes. So, under basic conditions, that's what we're after. Good deal. Thank you. What we want to do now, or are there any other questions before I move on? is introduce the concept of cell diagrams. Cell diagrams are a simplification on electrochemical equations that we are just writing. We're literally reducing it down to the entities that are actually undergoing redox, oxidation and reduction. Everything else has been removed. So in an electrochemical cell, this is the standard notation. On the left-hand side, you have the anode. Whatever is undergoing oxidation is on the left-hand side. Whatever is undergoing reduction is on the right-hand side. You work your way inwards from the electrodes. So the solid is a conducting electrode. If it's not, you have to put a conducting electrode in there. So you'll often see platinum or carbon added to give you an inert electrode. Solid, and everything is in contact with everything else. So if you remember the demo we did last day, there was bubbles that were forming on the solution of the aluminum. So solid is in contact with the gas is in contact with the solution as we move inwards, and the two solutions are connected through the salt bridge. And that's how a cell diagram is prepared. The phase boundaries from solid to gas to solution are separated by a vertical line, and the salt bridge is represented by double vertical dashed line. Oops, sorry. I don't remember. Do you need to write any of this down? Or do you have all of this? You have it? Thank you. So I'm just going to move on. And let's go back and do some examples with this. So we want to write cell diagrams for each of the following reactions. In order to do that, and I'm just going to start working with the ones that we've got here, you really need to know the two half reactions. So in the example that we have present here, I'll just start at the top. So if we were to go back to the previous notes, we would be able to identify the redox couples as being that and that. So I'm just going to scroll to the bottom and write the two half reactions. We have MnO4 minus reacting to give you Mn2 plus, and we have I minus reacting to form I2 solid. Those are the two half reactions where we were at. That's really all we need in order to write the cell diagram. We realize that this first reaction goes from +5 to +2, -1 to 0. -1 to 0 is, okay, +5 to +2 is a gain of electrons, so that's reduction. -1 to 0 is a loss of electrons, so that's the oxidation. So the anode is written first, which is the oxidation. And since we don't have, we're not sure if if iodine is a conducting solid, so we're going to put one in. So we have platinum in contact with iodine, comma separates the entities of the same phase. There, in contact, there is no gas, so we go directly to the solution, I minus. And that concludes the oxidation, or the anodic reaction. Then we go to the reduction. The solution, well, we have the manganese ions in contact with MnO4 minus. That's it. That is what is involved in the redox reaction, but we don't have an electrode here, so we're going to put an electrode. And so that is the cell diagram for this reaction. And represented as acidic over there conditions. Where did the platinum come from? When you don't have an electrode, you put an inert electrode in. So if I go back to here, these notes, the last one says, if conducting solids form the electrode, and in the example we have here, we clearly don't have an electrode for the manganese side of it. If there's no solid that's part of the redox, we put an inert electrode. Whether we put platinum, which is very common, or we put carbon, graphite, both of those work just fine. Does that make sense, Taylor? For the second reaction, which was this one right here, we had P4 going to HPO4, H2PO4 minus, and to PH3. So we had P4, which is a solid, going to PH3, which is a gas, and we had P4 solid going to H2PO4 minus. Just to figure out things out, that is -1 plus 3, 0, 0, -2 plus 1, that's plus 5. So let me try that again. I'm not awake. Plus 1 minus 3. That's better. 0, gain of electrons is reduction. Loss of electrons is oxidation. We aren't sure if phosphorus is conducting, and it would be really hard to make a wire out of it. So let's just create an inert electrode. Just for the fun of it, I'm going to use carbon, which is in contact with P4 solid. And from the anodic side of it, I have H2PO4 minus. We have our salt bridge. There isn't actually an aqueous solution, so it's ignored. PH3 is a gas. Onto P4 solid. And I'm going to put an inert electrode in there just to say that I have some electrical connectivity. And this is basic conditions. Why do we put the gas first for pH3? Because if we go back and look at the representation here, there is nothing in solution. And if you think about how the demo went the other day, it is literally the gas that is in contact with the H2PO4. So in the previous one, it was in contact with the aluminum. In this example here, the gas would be in contact with the H2PO4 minus in solution. So we're working outwards from electrodes to entities in gas phase, entities in solution, which are connected through the salt bridge. And this one just doesn't happen to have any reactive entities in solution. There's still stuff flowing through the salt bridge, but they're just travelers. They're not involved in the redox reaction. The redox reaction in this case is just the phosphine gas forming P4, or being formed from P4. Are there other questions on this? All right. There are two additional ones to do. And because I have given you the half reactions for this, I would like you to go through, and you have them right here. Endeavor to write down the cell diagram for that reaction as presented. Go for it. It would be hard to type all of that in. If someone's willing to come onto the chat and tell me what they've written down, I'll work through it with them, or multiple people, using voice. Anyone willing to do that? So which of these is the oxidation? Which of these is the reduction? The first one is the what? What's the first one here? It's reduction, yes. And the second one is the oxidation. Cool. So what do we need to write down for the oxidation half reaction? Anyone want to give it to me? Via voice would be preferred. So we have an alert electrode. Those are the entities in solution. Salt bridge, entities in solution, to our inert electrode. We were just doing that. To go in the reverse direction, to write the chemical equations for the following electrochemical cells, you literally need to break them up into the two half reactions and then combine the two half reactions together. So for the first one, now here these electrodes are reactive. Right, there's the only thing that's present that can possibly take part in the redox. So zinc goes to zinc 2 plus, copper 2 plus goes to copper, solid. The mass is balanced. In order to balance the charge, I need to put 2 electrons like that. Why do I use platinum? Because platinum is a traditional inert electrode. Has to be something that's going to be non-conducting. Platinum is standard because it's relatively non-reactive. And one can now simply add this thing together and get zinc solid plus copper 2 plus acts to give zinc 2 plus copper solid. The third one, I actually don't know why the I don't know why the hydroxide's there, but magnesium that's the cell diagram. One could break it up into the half reactions. And it's fairly clear that this is occurring under basic conditions. To balance the top one, I just simply need to add 2 electrons. Let me figure out why that's not doing anything. Hey, that's weird. I'm just calling up the program again because it actually crashed. There we go. So the first one is balanced. The second one, in order to balance it, it needs to be balanced under basic conditions. But it's pretty easy to look at this and balance this under basic conditions because you have hydroxide is a conserved entity, actually. And so we now have 4 hydroxides on the right-hand side. To balance the charge, one sits there and looks at this and goes from -1 to -4. I need 3 electrons on the left-hand side. So to balance the number of electrons, I'm just going to cross multiply. 3, 3, 6, 2, 6, 2, 8. And of course, electrons cancel, and that's it. There we go. And that is the balanced half reaction. The balanced chemical reaction. Are there any questions on that? Okay. Oh. What we've done to this point is just go over the electrochemical conventions, probably introduce the idea of cell diagrams to people, but that's the basis for electrochemistry. What we're going to do now is we're going to start making links between electrochemistry and thermodynamics and equilibria. So the relationship with thermodynamics comes from Michael Faraday, who a long time ago, and remember, I'm not too concerned about dates, Michael Faraday derived a relationship between work, number of electrons, and the electrochemical cell potential for a system operating reversibly. What is meant by reversibly? It means that the reaction is proceeding infinitely slowly. It's not drawing concentration gradients or anything like that. So in the context of an automobile battery, if we're going to do electrochemistry, when you go to start your car, the battery, you're drawing a couple hundred amps from the battery. That's not a reversible process. But if you use that battery to maybe have an LED going in the vehicle, that is an infinitesimally small draw from the battery, and that would be a reasonable reversible process. So Faraday's relationship says that the reversible work is equal to the number of electrons transferred times Faraday's constant times the electrochemical cell potential. Faraday's constant is simply the charge on 1 mole of electrons. So you could actually calculate this if you know the charge on an electron and multiply by Avogadro's number. Faraday's constant is simply 96,485 coulombs per mole of electrons. And I already talked about the idea of reversible in the context of an automobile battery. Drawing a very, very small current for a small application would be considered a reversible process. If we get back to that definition of a system operating reversibly, and we start linking or thinking back to what we discussed in thermodynamics, we will recall that the Gibbs free energy was the maximum work that a system can do and still have a spontaneous process. And if you go back and look at the derivation, it assumed that you were working through you were working with a system that was maximum work cloud system at equilibrium, not at equilibrium. Yes, sorry. Anyway, the relationship is the maximum work is from both thermodynamics and electrochemistry is the same. So delta G, which is a function of temperature, is equal to the work that we have here. So we have two relationships that we can draw from this under standard and non-standard conditions. Delta G non-standard, NF E cell. Delta G standard is NF E naught cell. This is the link between thermodynamics and electrochemistry. If we have a free energy, we can calculate a cell potential. If we have a cell potential, we can calculate a free energy. The other thing that comes out of this is that because the Gibbs free energy is temperature dependent, so is the cell potential. So thermodynamic values for cell potentials are tabulated at 298 Kelvin. That's the ones that are in your data table. And they're only valid at 298 Kelvin. So if you're operating at any other temperature, you need to calculate the cell potential at that temperature. How do you do it? This is the equation that you use to calculate it. If you can calculate delta G, you can calculate a cell potential. So we're going to actually take this knowledge and derive an equation for calculating the voltage under any condition. And happens to be called the Nernst equation, which you have probably seen in high school and definitely saw in the lab. So the equation that was just written there was, no. That was our equation for the free energy relationship. We also have now delta G is equal to minus number of electrons, Faraday's constant, times E cell. And of course, both of these are temperature dependent. We're going to take this relationship and substitute it for the non-standard and standard conditions. And that gives us the relationship minus number of electrons, F, E cell, plus RT log Q. To simplify this a little bit, we're going to multiply through by 1 over n and number of electrons times F, the negative of that. And that's going to give us E cell minus RT over NF natural log of Q. Now, just for fun, not really, electrochemistry is commonly reported as the base 10 log rather than the base E natural log. So to convert that to log, we have the relationship that the natural log of x is equal to natural log of 10 times log of x. That would be given in a math class. I'm not going to go through the derivation of that. Natural log of 10 is 2.303. So that is equal to 2.303 log of x. Which means our final expression is E cell and that is called the Nernst equation. That's the expression right there for the Nernst equation. You may have seen this value or this expression, but it is also commonly reported at 298 Kelvin. So before I ask about questions on this, I'm going to go through and we're going to calculate the Nernst equation at 298 Kelvin. So the only thing that we really are going to concern ourselves with is this expression right here. That's the one where there's a temperature dependence. So we have 2.303 RT. And what do we have to type in there? R is equal to 8.314 joules per mole Kelvin. Of course, the temperature is 298 Kelvin. And we have Faraday's constant, 96485 coulombs per mole of electrons. All of this is substituted in there. Oh, one more final thing. If you're just following the units through, you'll realize that there's a little bit of a discrepancy here until you go back to physics and realize that a volt is actually a joule per coulomb. So when we put all the numbers in, you have 2.303 R, 8.3114 joules per mole Kelvin, times T, 298 Kelvin, times 9 divided by 96485 coulombs per mole of electrons. Moles cancel, Kelvins cancel, and if we realize that Coulomb is now joules per volt, that becomes joules per volt. Joules cancel. And we end up with the value 0.05916 volts over number of electrons. Haven't dealt with the number of electrons. That's still a variable. There we go. And this is the Nernst equation at 298 Kelvin. Now I'm going to ask, where have people seen these in high school, and which one? the complete one up above, that Nernst equation right there? Or have you seen the 0.05916, which is valid at only 298 Kelvin? Oh. It was in one of your labs, was it not? Okay. All right, so these are new to most people. Yeah, we got completely lost. Okay, well, I'm going to start applying them. So the next thing I want to do is an example that involves this. And this example looks fairly easy until, well, you're going to see as we go through this. First of all, we're working at 10 moles per liter sulfuric acid. And we have this, at least we're at 25 degrees Celsius, which is 298 Kelvin. That's good. We have this chemical reaction that we ultimately need to balance. All right. So to apply this, it's going to take a bit. We have enough time. It might take a minute or two over. My apologies. We have the reaction of lead plus lead oxide, lead 4 oxide. And this is in the presence of sulfuric acid. This is a car battery, which has sulfuric acid. And the equilibrium is PbSO4, which is also a solid. If we assign oxidation states to all of this, it's 0, -2, +4. The sulfate group is -2, and we're going to see that it's conserved throughout, so I don't need to worry about it. And that means the lead is +2. Going from 0 to +2 is the loss of electrons, that's oxidation. Going from +4 to +2, gain of electrons is reduction. I need to realize also that sulfuric acid is my source of the sulfate ion. And so in terms of the two half reactions, I have lead plus sulfate from the H2SO4 reacts to give PbSO4, solid. I also have lead oxide let me reset that. These are going so well up until last day. Okay, good. Don't even start on me. I'm talking to the computer. Okay, so we have that. We need to balance each of these processes. In the first one, lead is balanced, sulfate is balanced. In order to balance the charge, I need to add 2 electrons to the right-hand side. That wasn't too bad. For the second one, lead is balanced, sulfate is balanced. I balance the oxygens by adding water. I balance the hydrogens by adding H+. And so now the mass is balanced. To balance the charge, I have got neutral on the right, 2+. I need 2 electrons on the left. The electrons cancel, and I do need to calculate cell potentials, and I'm going to do that in just a little bit. So eventually I'm going to get a reduction potential there and a reduction potential there as well. But for now, I'm just going to add everything up. And I have lead solid plus PbO2 is a solid. plus 2 sulfates plus 4 H plus reacts to give 2 PbSO4 solid plus 2 water. Just to verify, 2 leads, 2 leads, 2 sulfates, 2 sulfates. On the left-hand side, there's 2 oxygens, 2 oxygens, 4 hydrogens, 4 hydrogens. It's balanced, neutral on both the left and right. Because of time, I'm just going to give you the reduction potentials. Negative 0.356 volts and 1.690 volts. So the standard cell potential is, of course, cathode minus anode. And if we go back up here and look at these, loss of electrons is oxidation, gain of electrons is reduction. Just which side of the equation they're on? Are they on the left-hand side of the electrons are on the left or the right? Gain of electrons is reduction, and this would be equal to 1.690 volts minus negative 0.356 volts is 2.046 volts. That is the standard cell potential. But we're operating under non-standard conditions. We're operating at 10 moles per liter. And so to calculate the cell potential under non-standard conditions, we have the expression that is the Nernst equation. So what do we have? We know the standard cell potential. We got that. We just did that. We know the number of electrons because we can go back up and look at any of the half reactions, and we find that 2 electrons are transferred. So it's a 2-electron process. We can also get Q from the balanced chemical equation. So if we look at our balanced chemical equation and start realizing that we don't need to care about the solids and we don't care about liquid water, what's left is this, the sulfate and the hydrogen ions, in terms of developing Q. And so Q is 1 over the hydrogen ion concentration to the 4th power times the sulfate concentration squared. I'm going to take about 3 minutes after class to finish this off because it's a full example and I don't want to interrupt it except for this crazy thing. In order to calculate these concentrations, I now need to go to equilibria and realize that sulfuric acid is a strong acid. And so if we write an ice table for sulfuric acid, we start off with 10 moles per liter of that. And it goes to completion. But that still doesn't give me sulfate. In order to do sulfate, I need to do this one more time. HSO4 minus is in equilibrium with H plus SO4 2 minus. The Ka for this is 1.1 times 10 to the minus 2 moles per liter. So we have a nice table here, and taking the values from above, 10 moles per liter of that, 10 moles per liter of that. We don't have any sulfate. That's what we're trying to figure out. The equilibrium constant favors the reactants. Given my initial conditions, I have a 0 on product, so I am starting on the side favored by the equilibrium constant. That's an X, that's an X, that's a minus X. And that is the equilibrium constant I need to solve. Oops. Because the equilibrium constant is not extreme, making an approximation won't work. So I'm just going to substitute it into solver, and I get a value of X of 0.011 moles per liter. Please work. Good. We go back up to the table here. The two things I needed to figure out were the sulfate concentration and the hydrogen ion concentration, being X and 10 plus X respectively. So for hydrogen ion is 10 plus X, which is equal to 10.011 moles per liter. But because of significant digits, this is just actually equal to 10 moles per liter. The amount contributed by the second dissociation is negligible, but the sulfate concentration, which is just simply X, 0.011 moles per liter, is not negligible. So we now substitute that back into, and this is the last step, 2.046 volts minus the number of electrons transferred is 2, times log of Q, and Q was 1 over the hydrogen ion concentration to the 4th power, times the sulfate ion concentration squared. After all that, 2.049 volts. And the reason why it's not a huge change is because of the log relationship. The log relationship there means that cell potentials don't change a lot as a function of temperature. They do change as a function of temperature, as we see here, but it is not substantial, as we see with free energy, which changes quite a bit. That ends it for today's class. I thank you for your patience and going a few minutes over. We're going to continue this next day with a demo. So I'll see everybody on Friday. I also am going to hang out here if there's any questions. So I'll be here for a bit. Thank you.